All right, I did a survey about a year ago almost, and most of the people said they want to see more computer science shit on this channel. So to keep to my promise, this is the beginning of that stuff. I'm sorry it took a year, but this is it. This is the savage scientist Ed right here, and I do Uber and police car. All right, now that we discussed arrays, let's talk about lists now. A list is a link-based collection of the same data type. So that means we're gonna have the same data types in our declaration. See here we have characters that's gonna be used in A1. That's why it spells out savage. And in A2 we can have 378. That's also characters, and we can have integers in A3. So this is what the declaration part of the statement look like. Let me brighten this up so you can see the actual L in list. And this is what this looks like in memory. As you can see, this is definitely a mess. So let's see where everything is. This is part of A1. A1, and this is linked here like this. This is linked to the A. And then it's going to be linked, the A is linked to the V. SAV, and then it's going to be linked to the other A. SAVA. And then this A is linked to the G. And then the G is linked to the E. Very, very confusing at first, but it's just a linked based system. And the data structure in A1 is mechanisms to control how this stuff is linked together. So just look at a linked list, which is why it's called a linked based collection of data. Is just the way that we get from the S to the A through links. And the same thing with the 378. So we start here, the 3, and then it's linked to the 7. See that? And the 7 is linked to the 8. And we also have 273 and 901. So 273 is right here in memory, and it's linked to the 901. That look like spaghetti. It really do. It look like some red spaghetti. So this is what a linked list will look like in your 2 gigs of memory. Now, this is just a representation. Do not assume this is how it really looks in memory, because when you look further into this, it's a hell of a lot more stuff going on in your memory than this, but this is a simple representation of a linked list. So why would we even use linked lists is the question in your mind probably. So a linked list has this advantage because you could create stacks, queues, trees, and hash tables based on the links we have here. An array, once you hit the end of an array, that's it. You'll have to create an entirely new array to add savages. If I want to create the word savages and add this S to the end, that means I could just go to the E and then link it to the S. In an array, I would have to create an entirely new array of the size savage plus 1. So I'm going to create a new array of the size 1, 2, 3, 4, 5, 6, 7, and then put the S at the end. And it may be a little easier for you to follow these links by color coding them a little better. So the 3 is linked to the 7. That's linked to the 8 right here. And the 273 is linked to the 901. And you can see the savage all over the place. You got the S, which is, all these are linked, like all the word savage is denoted by the red links here. S-A-V, S-A-V, A-G-E. S-A, what the hell is the V? V-A-G-E. And I also added this extra link to the S here because it became savages. Alright, so when it comes to lists, you can't talk about a list without talking about an iterator, or a way to move a route in a list. So an iterator will have the start location, the current location, and the end location. The end location could also be represented in the list by using the NULL character. And I'm going to show you two different ways that this is represented in the list using my three examples, A1, A2, and A3. So we're going to start with A1 that has the word savage and is of type character. So you're starting off this list with the iterator. The iterator is going to point to the start. So that's why I got iterator start at 22. So at 22, you see that's the S in savages. And then once you in 22, then it's going to point to 14. So we're going to go from 22 to 14, 2, 2, 1, 4. That's going to give you the A. When you're at the A, it's going to point to 25. See that? 2, 5, that's the V right here. So at 25, then it's going to point back over here to this A at 32. And then the A is going to point all the way back to the G. And then the G is going to point to the E. And then I added this piece to it, but I'm going to take this off because I don't want to have to redraw all this stuff. So there it is. That's the word savage right there. Everything points to everything, and that's why it's written in this notation. This is the data and this is the location in our memory. The iterator is going to start at the S at 22 and go all the way to the E. And once it gets to the E, the current state is then going to change back into the front of the list at 22. And I know that because look here, the E is pointing back to 22, which is the same position as the iterator start. So, and that could be done programmatically through logic. So when we get to a programming language, I'll show you more about that. But right now, I'm just trying to show you a higher level view of a linked list or a list. So let's go to the A2, which is holding a value 3, a 7, and an 8. This is just characters, 3, 7, 8. This is not the number 378, so you can't add to it and get 379. So the iterator is going to start off with start off with the 61 location. That's going to have the 3. When we get to the 3, it's going to point to 33. And when we get to the 7, it's going to point to 47. When we get to the 8, it's going to point to null. This is the symbol for null. Null just means nothing. So let's take a look at it. 3, 7, and 8. And you can see its location. This is at the iterator start pointing at 61. Then it's going to point over. Then the 3 is going to point over here to 33. And then it's going to go to 47. And let's notice this iterator is going to have different behavior because when you get to the 8, it's going to point to a null character or a null symbol. And that's telling the iterator that you have reached the end of the list. And this is the traditional way that a linked list works. The null character at the end signifies the end of the list. Now let's take a look at A3. A3 has two values, 901 and 273. I don't know why I keep saying that 901 first. 273 and 901. At location 17 is the value 273. And then at 273 is going to point to location 34 that has the value 901. And then once I get to the 901, it's going to point back to location 17. That's going to take us back to the 273. And it's going to have type integer. That just means that these values can be manipulated mathematically. So they are not symbols. These are real numbers. And this is where it's at in memory. That's the 273 pointing to the 901. And you can see their locations. So one of the biggest things about this is this thing I call O notation, or people in computer science refer to this as O notation. This just tells you how much work your algorithm is going to do to perform certain functions. I'm going to discuss that later, so don't really get too involved in this, but remember that if you have an array and you want to change a value in it, it's going to happen instantly. And if you have a linked list and you want to change a value, you're going to have to go through the entire list until you get to the one you want. So if I want to change the V, I'm going to have to start with the S, then I'm going to have to go to the S, move to the A, then move to the V, and then I change it. In an array, I could go straight to the V. So let's keep it simple and move on to the stacks, the queues, the trees, and the hash tables.